In this video, we're going to be talking about how we can find the volume of a solid that's rotated about any line. So the axis of rotation is no longer either the x or the y axis. It could be any vertical or any horizontal line, depending on how we rotate. So we're going to start off by looking at how we can do this using the disk method, and then we'll go through the washer and shell methods. So the way that our equation changes because we're rotating about a different line is that now the radius of our disks is now the distance between our axis of rotation and our graph. So if we look at this pink region, we're rotating about y equals -2 here. So the radius of our disk is going to be whatever the distance is between this vertical line and our function, x squared minus 2. So if I subtract the top coordinate from the bottom coordinate, then I get that distance. And now I can use that as my radius. So we're going to do our function minus the axis of rotation, or the output on this graph, minus the value here gives us the distance between those 2 points. So that's all we need to do to change our disk method equation. Again, you can look at the graph to find your intersection points, or you can set your two curves or boundaries equal to each other. So I know I have f of x here and this horizontal line. So I can subtract those two things, or set them equal to each other, and find the intersection point. And when we do that, we see that we are intersecting at x equals 0. That's our vertical line there. We're also told we're bounded by the vertical line x equals 2. So now we're trying to find this area so that when we rotate it and spin it around this vertical line, we can get the volume of that solid. So we know we get our radius squared by subtracting our function from our new axis of rotation. So that leaves +2. -2 just leaves 0. So we just got x squared squared. And simplify that to x to the 4th. Now we can find our antiderivative and evaluate our integral. That's x to the 5th over 5, and we're going to evaluate that at 2. If we evaluate it at 0, it's just 0. So we just get 2 to the 5th over 5 minus 0 is 32 fifths. And multiply pi for our last step. There's our volume. So not much different as long as you can visualize that the radius is just the difference between those two coordinates. Let's try out the washer method. So the washer method is going to get basically the same change as the disk method, but it's going to happen twice. So we have this horizontal line, y equals 2 again. We have our two curves, y equals x and y equals x squared. Y equals x squared ends up being the outer curve. Y equals x ends up being the inner curve. So let's figure out what we need to change about our washer. Well, if this is our center of rotation right here at y equals 2, then the inner radius, or the hole's radius, is going to be the distance between that vertical line and our inner function. So if I subtract my inner curve, or do my inner curve minus the axis of rotation, subtract the axis of rotation from the inner curve, and square it, then we can get the circle of our hole. And now if we find the outer curve and find the distance from our axis of rotation to the outer curve, that would be our outer radius. So we take our outer curve and minus the axis of rotation there, and then square it, and then we can get the area of our outer circle, which represents the area in between our two curves. Now we can rotate it and find the volume. So again, finding the intersections, you can look visually at the graphs, or you can set your two functions equal to each other. And we can find that our intersections are happening at x values of 0 and 1. And we can verify that on the graph. So now all we need to do is take our outer curve minus our axis of rotation, so x squared minus 2, and square it. Take our inner curve, which is our x curve and subtract our axis of rotation, so x minus 2, and then square it. So squaring this binomial gives us x to the fourth minus 4x squared plus 4. Squaring this binomial gives us x squared minus 4x plus 4. We're subtracting that entire polynomial there, so make sure you distribute that negative throughout. And when we simplify, we end up with x to the fourth minus 5x squared plus 4x. That's what we're going to antiderive and evaluate. So find the antiderivative, evaluate it at 1 and at 0, subtract those two values, and multiply by pi when we're all finished. And we end up with 8 pi over 15, or 8/15 pi. All right, the shell method is the one that gets a little bit trickier here, but it's still basically the same concept we've been practicing. The shell method says that the volume is 2 pi times the integral from a to b. We need to find our shell radius and our shell height and multiply those. So to find the shell radius, given this example, the radius of our shell is going to extend from our axis of rotation, which is x equals -1. So here's our center of rotation. So the radius of our disk is going to be the distance from there over to whatever x value we're evaluating at. So we could say that the difference is our distance between those 2 points. So if we do x minus our axis of rotation, that should generally give us a positive value. We always want our distance to be positive. But just in case, we could put absolute value bars around that. And then it doesn't matter which order you subtract. We want to find the distance between these 2 points, the x value minus our axis of rotation, or we could do our axis of rotation minus our x value, but that gets a little bit trickier. Always try and get a positive value. Always set it up to get a positive value there for our shell radius. We want that distance to be positive, and then it makes it much easier. So we're going to do x minus our axis of rotation, so x minus -1. To find the shell height is going to be the difference between our functions, because our shell needs to fit within the area between those two curves. So we just need to subtract the top curve from the bottom curve, or I'm sorry, subtract the bottom curve from the top curve minus the bottom curve, there we go. And so that should be y equals x is our top here, x squared is our bottom, so x minus x squared. We need our intersection points to figure out where we're going to integrate from. So you can do that using the graph. We can see that we intersect at 0 and 1, or you can set those two functions equal to each other to solve and find their intersections and verify. So we are integrating from 0 to 1 using our shell method. X minus -1 is x plus 1. Now we're going to distribute or FOIL these two binomials. That leaves us with x squared minus x cubed plus x minus x squared. And if we find the antiderivative of that after we simplify and evaluate at 1 and at 0 and multiply by 2 pi, we finally end up with 1/2 pi, or pi over 2, for our volume. So again, with volume of solids, looking at the graph, sketching it out, trying to figure out what these pieces are is really the tricky part, and it's always best to visualize it first. If you can do that, then setting it up and plugging it in and evaluating should be the easy part.